So 18.3, simplifying radical expressions. We're first going to look at the concept multiplying properties of radicals. Then we're going to look at how to simplify them using the multiplication property, and then how to simplify using order of operations. So concept 1, multiplication properties of radicals. So all this is saying is that if we have the radical of one number and it has the same root as the radical of a second number, we can combine them into one radical. Okay. And I have the proof for those who want to see. This is not going to be tested. This is just something to show you how this works. So if we have the nth root of a and b, that's the same as saying a and b to the 1 over n power. So remember, last notes we learned how to convert radicals into exponents. And we know that the property of exponents say that we could give that exponent to everything inside the parentheses. And we could rewrite this into radicals, showing the nth root of a and b. So this is showing how when combined under one root, that's the same as giving that root to each term, as long as everything is being multiplied. Okay. We're going to use that skill in concept 2. In concept 2, we're simplifying using that multiplication property. So in order to simplify, we have to know what each part of the radical is labeled as. So for example, if we had the third root of 6, we say that this 3 here is the index. So all I'm doing is labeling some vocab. So whatever that nth root is, that's the index. And then whatever is under that radical is called the radicand. Okay. So in order to simplify, we have to follow these rules here. So these rules. These rules state that the radicand has no factor raised to a power greater than or equal to the index. So what that means is that if we had an exponent inside of the radical, using our example of third root 6, we could only have a root of an exponent of 1 or 2, because it has to be lower than the index. So that's what that one's saying. The radicand does not contain a fraction. So this number here inside of the radical cannot be a fraction. It has to be a whole number. And then lastly, there are no radicals in the denominator of a fraction. Meaning if I had the fraction 2 over the square roots of 3, we could not simplify this because there is a radical inside of the denominator. So that's what these 3 rules are talking about. And we'll see that more in the examples. Okay. So looking at the first example, it says the example below are radicals that are not simplified. Which condition does each example meet? Okay, so these are examples that cannot be simplified, and we're going to say it either meets rule 1, 2, or 3, what we just went over. Okay, so looking at part A, we have the third root of x to the 5th. Why can this not be simplified?
Because the nth root is larger than the radicand. The exponent that's in the radicand is larger than the index.
Correct. So this number right here, that exponent of 5, is larger than the index of 3. So we would say that since 5 is greater than 3, according to Rule 1. Or was that Rule 1? Yes. According to Rule 1, that's the reason why it cannot be simplified. So since 5 is larger than 3, according to Rule 1. Okay. Why can't B be simplified? It's a fraction, and what rule says we can't have a fraction? Rule 2. So since the radicand is a fraction, and this is according to Rule 2. Okay, so we said A can't be simplified because the exponent is greater than the index. B cannot be simplified because the radicand is a fraction. Why can't C be simplified? Good, since there's a radical in the denominator. Since there is a radical in denominator, and that's according to Rule 3. So these are the reasons why they cannot be simplified. Okay. Cannot be simplified. So these examples were just showing us how the rules were applied. All these can't be simplified. Looking at the first example, it says simplify the expression assuming that x is greater than or equal to 0, the expression square root of x to the 9th power. Why is it adding this part for us? Assuming that x is greater than or equal to 0. Why is that important? Good, because the opposite of x is greater than or equal to 0 would be x is less than or equal to 0, which would be negative numbers. If we had to assume some of these x values was negative, that means some of our answers would be imaginary. But they don't want us to deal with that. We're only dealing with real numbers. So the way we need to simplify this is we need to rewrite the square root of x to the 9th as some of those perfect squares. Remember you had that chart on the last notes? So we could write this as x to the 8th times x. Because x to the 8th times x is still x to the 9th. I just separated one x out of it. And I did that because I could rewrite x to the 8th as a perfect square. How would I write that as a perfect square? If you're not sure, check back on the chart. How can I write x to the 8th as a perfect square? So it's going to be some part here squared times my x. X to the 4th, correct. X to the 4th. Because x to the 8th is the same as saying x to the 4th squared. Because the property of exponents say that we multiply these exponents together. Okay? Now using the property we just learned, we can separate this radical into two parts. We could separate this into the square root of x to the 4th squared times the square root of x. Okay. Is anything going to cancel in this statement?
The square and the square root of the first term.
Good. This square and this square root cancels. So that means we are left with x to the 4th times the square root of x. And we would just write that as x to the 4th in front of the square root x. Okay. So this is as simplified as it can get. So we took the square root of x to the 9th and reduced it to x to the 4th square root x. Make sure you have whatever number you get without that square root in the front. If you write it in the back, I'm going to assume that it is under this square root. So it has to be written in the front. Think of it as your whole number. Write it in the front. Okay, so the only important concept here is you have to remember your properties of perfect squares. And that is on that chart on the last notes. Okay, any questions on 2? Okay. So now on number 3, we're going to be doing the same thing. We're going to be reducing each of the radicals, and we're assuming that all the variables are positive real numbers, so none of them are negative. Okay. So notice on part A, instead of the square root, we have the 4th root. Okay. There's several ways to go about this. I'm going to show you 2 different ways, and you're going to choose whichever method works for you. The first method, so I'm going to label this as method 1. We could rewrite this radical like this. So the 4th root of b to the 7th is the same as writing b how many times? 7 times. 3, 4, 5, 6, 7. Okay. If we were to simplify this, the 4th root tells us that we can only take out pairs of what? 4. So I'm going to go, go here, and I'm going to highlight pairs of 4. How many pairs of 4 do I have? Just 1. So I am going to take out 1b from that pair. So I'm going to have b, 4th root of b times b times b. How can I simplify those 3 b's under the radical? b times b times b is the same as b cubed. So this is b, 4th root of b cubed. Okay, this is our answer here. This is our simplified answer. Okay, so that's method 1. Okay, method 2. Is instead of writing all our b's out, we're just going to separate them by the exponents. So that means that the 4th root of b to the 7 can be written as b to the 4 and b to the 3. Because the property of exponents say if we are multiplying the bases that are the same, we can add the exponents. So this is the same as saying 4 plus 3, which is b to the 7th. Okay. From here, we know that we could separate the radicals. We could separate the 4th root of b to the 4th times the 4th root of b to the 3rd. Once we separate the radicals, we see that the 4th root and the exponent of 4 cancel. So we're left with b, 4th root of b cubed. Notice we get the exact same answer. So these are just 2 different methods you could use. If this concept confuses you, I would stick with method 1 because it's more visual. If you understand the concept a little better, then stick with method 2. Okay. For this one, I'm going to be doing method 2. Okay. Any questions on the 2 different methods? So it's based on preference on what you're going to do on the exam. Now we're looking at part B. So we have the cube root of w to the 7th and z to the 9th. Okay, for the rest of the notes, I'm doing method 2. So I have the cube root of w to the 7th. So I need to take out as many w to the 3rds as I can. So I have w to the 3rd, w to the 3rd. So far, that's only 6 w's. And this is w to the 7th, so I need to write another w. Okay. Then I need to take out the pairs of 3's from z to the 9th. So I have z to the 3rd, z to the 3rd, that's just 6 z's. And then z to the 3rd again is my 9 z's. So under this radical, I am showing you 7 w's and 9 z's. Okay. Then I'm using that property that says we could split this up into several radicals. So this is the cube root of w cubed, cube root of w cubed, cube root of w. So there's my w's. And then I have the cube root of z cubed, cube root of z cubed, cube root of z cubed. So now I took my 1 radical and I split this up into 6 radicals. I know my radicals will cancel with the exponent if the numbers are what? They're both the same. So right here, these cancel out because they're both 3's. The only one that does not cancel out is that cube root of w because it does not have an exponent of 3. All these ones that cancel out, we are left with just that one variable. So I am left with w times cube root of w times z times z times z. How could I simplify this? I have 2 w's, so that's the same as saying w squared. How many z's do I have? 3, so that's the same as saying z cubed, and then I write my cube root of w. So this is the simplified version of our original problem on B. Any questions on that example? Okay. Now looking at example C, we just have the square root of a number. When we need to simplify a square root, we use the prime, what is it called? The prime factor tree. So remember, we are dividing into 56 using our prime numbers. So what's the first prime number that can go into 56? 2. Remember, our prime numbers are, you rewrite them, 2, 3, 5, 7, 11, etc. And we always start with the smallest first. So 2 goes into 56 28 times. What prime number goes into 28? 2 goes in 14 times. What's next? 2 goes in 7 times. Is 7 prime? So we circle it. That means we're done. We ended with 2 prime numbers. Since this is the square root, we're going to be circling pairs of what? 2. Because remember, on the square root, we have that imaginary 2 there. So we are circling pairs of 2. So we have a pair of 2's here, Do we have any other pairs that we can circle?
No.
No. Remember, the pair that we circle, we take out one of them, and that goes where? Outside of the radical or inside?
Outside.
Outside. So this is equal to 2 square roots of, what goes on the inside?
I would think it's those still multiplied, so it'd be 14.
Correct. So it's whatever prime numbers are left over, we multiply them. So 2 times 7. So this is 2 square roots of 14. This is our answer. So all we're doing is reducing the square root of 56 to 2 square roots of 14.
So for that one, had there been another pair of 2, it would have been 4 on the outside.
Correct.
Okay.
So
like
all-
whatever pairs you multiply them together as well.
Correct. Correct. So she's saying if there was another pair of 2's here, then I would have to take out an additional 2, and it would go here, 2 times 2. So that would be 4. So the amount of pairs you have, you take out one number from it, and you use it to multiply. Okay. Now looking at part D, we have 6 square roots of 50. When we do the prime factor tree, are we going to deal with the 6 in the beginning?
No.
We're only going to do the prime factor tree of what number? 50. So what's the first prime number that can go into 50? 2. So 2 goes into 50 25 times. Can 2 go into 25?
No.
No, so we go to our next prime number. Can 3 go into 25? No, then we go to the next prime number. Can 5 go into 25? Yes, so 5 goes into 25 5 times. So we end with 2 prime numbers. Okay. So since this is the square root of 50, we are circling pairs of 2. So what is our pair?
5.
The 5s are our pair because they're both the same. So that means I'm taking out a 5. And what's left on the inside? 2, because that's the only prime number left that did not have a pair. Okay. However, we had a 6 also on the outside. So what do you think we're going to do with this 6 and the 5? Multiply. So 6 times 5 is 30. So this, that 6 square roots of 50 is the same as saying 6 times 5 square roots of 2, which is 30 square roots of 2. This is our answer. So if we have a whole number already on the outside of our radical, we are just multiplying that whole number by the answer that we get. Okay. So we talked about what to do when we have variables, what to do when we have numbers. Now we're looking at a problem that has both numbers and variables. Okay. So what I would do first when I have numbers and variables in one problem is I would use that property of radicals and I would separate each of these. So I have the cube root of 40, the cube root of x cubed, the cube root of y to the 5th, and the cube root of z to the 7th. Okay, all I did was give that cube root to each part of my problem. Okay. Now we know how to separate each one. So for the cube root of 40, what are we going to have to do with that 40?
Prime factor tree.
The prime factor tree. So what goes into 40, the smallest prime number? 2. So 2 goes in 20 times. What goes into 20? 2, 10 times. What goes into 10? 2, 5 times is 5 prime? Yes, so that means we end our prime factor tree because we stopped at 2 prime numbers. And since this is the cube root, we are going to be circling pairs of 3. So we have 1 pair of 3 here, and those are the 2's. So where is that 2 going to be? On the outside or the inside? Outside. So cube root of 40 is the same as saying 2 cube root of 5. So we did the first part. What do we see that's happening on that second part? What's the cube root of x cubed? X. Why? Good. These cancel. So that means we're just left with x. So times x. 'Cause remember, all these are being multiplied. Okay. How could we simplify the cube root of y to the 5th? How can we rewrite y to the 5th?
Y to the 3rd, y to the 2nd.
Correct. So y cubed and y squared. So if we separate this, which one cancels out? The first one. So that means for this one, we're left with times y cube root of y squared. Because we can't simplify the cube root of y squared. How would we write z to the 7th? So we want some z cubes in there. So it would be z cubed. That's 3 of the z's. What's next? Z cubed, and that's 6 of them. And then what else? Z. So that means if I was to separate this, this would be the cube root of z cubed, cube root of z cubed, and the cube root of z. Which ones are going to cancel? The first two, because they have the same root with the same exponent. So that means I have times z cube root of z. Okay. Even though this is my answer, I have to simplify this. Okay? So what I'm going to do is I'm going to look at each part. So I have one number on the outside, and that's 2. Okay? How many x's do I have on the outside? 1, so I'm just going to write x. How many y's do I have on the outside? 1, so 1 y. How many z's do I have on the outside? 2, so that's z squared. Okay, now I have no more terms on the outside, so I'm going to write my cube root. And what parts do I have under the root? So I have a y, so I have a 5, a y squared, and what else? A z. This right here is my answer. So once I get all the separate answers, I have to combine it into one. So I take everything that's on the outside, place it on the outside. Everything that's inside the radical, I place it on the inside. Okay. Any questions on how I went from the original problem to the answer? Where'd I get which part in the front? Oh, this part? I just looked at everything that was in the front in this answer. So I had a 2 in the front. That's where the 2 came from. I had an x and the y in the front. So that's where they came from. And then I had 2 z's in the front, which I wrote as z squared. Now let's look at concept 3. So concept 3, we're now going to be simplifying the radicals further using the order of operations. So if you remember order of operations, there's the acronym PEMDAS. this is the proper way to write it out, because even though, because this is usually how you see it, PEMDAS, even though multiplication comes before division and addition comes before subtraction, we read it whatever comes first, left to right. So that's why it's written like this. So whatever comes first, left to right. So if you remember, P stands for parentheses. Okay. E stands for exponents. M is multiply. D is divide. A is add. S is subtract. Okay. So when we're going through PEMDAS, once we get to the part where it's multiplication and division, whatever comes first, left to right. When we get to the part that's addition and subtraction, it's whatever comes first, left to right. So just like how you read, left to right. So using the order of operations, we're going to simplify A. Okay. So in order to simplify A, we first go through each one. So we go through parentheses. There's no parentheses here. Then we look at exponents. So we do have exponents in this problem. And that exponent part comes from here, the a to the 7th divided by a cubed. What's the property of exponents when we're dividing? What do we do to the exponents? Subtract. So we could rewrite this as the square root of a to the 7th minus a to the 3rd, which simplifies to what? A to the 4th. Okay? A to the 4th, since we want to get pairs of 2's, because this is the square root, we could write that how? Square root of what? A squared times a squared, because a squared times a squared is a to the 4th. We add the exponents when we're multiplying. Okay. And then we learned that with the properties of square roots that we could separate them. So the square root of a squared times the square root of a squared means what happens to both these radicals and exponents? They cancel. So I'm left with a times a, which is the same as a squared. So that means the answer to the square root of a to the 7 divided by a to the 3rd is a squared. So this is us using order of operations and the properties of exponents. Okay. Any questions on the first part? Okay, now looking at part B, we have the cube root of the fraction 3 over 81. Can we reduce this fraction 3 over 81?
Yes.
What could it reduce to?
1 over 27.
1 over 27. So this is the cube root of 1 over 27. What would be the next part, knowing the properties of radicals, the properties of these roots?
Find the cube root of each denominator.
Correct. We're going to find the cube root of 1 and then the cube root of 27. So what we could do is we could give that cube root to the numerator and give it to the denominator separately. Okay. What is the cube root of 1? 1. Good. Anytime we have a 1 by itself in there, the answer is just 1. Okay. And then the cube root of 27 we can find using that prime factor tree. So what's the first prime number that goes into 27? Yep, 3. Then we're left with 9. What's next? 3. And we're left with 3. Since it's the cube root, we're circling pairs of 3. And notice how we just have one pair of 3 with nothing else left over. Meaning the cube root of 27 is 3. So that means our answer here is 1/3. Okay. Or you could always check on your calculator, do the cube root of 27. If you get a whole number, that's fine. If you get a decimal, then I need to see the prime factor tree. Part C, we have 7 square roots of 50 divided by 10. What do you think our first step would be? What do you think our first step would be?
Simplify the numerator.
Good, simplify the numerator, and how would we do that?
Prime factor tree of the square root of 50.
Good, so we're going to take the square root of 50 off to the side and do the prime factor tree. So what's the smallest prime number that can go into 50? 2, and then we're end up with 25, and then what's next? 5, and we end up with 5, which are both prime numbers. So since we're doing the square root, we have to circle pairs of 2. So that means this simplifies to what radical? Good, 5 times the square root of 2. Whatever our pair is, we take one number out and that goes in the front. And whatever did not have a pair goes on the inside. So I am going to rewrite this problem as 7 times 5 square roots of 2 over 10. Because all we did is that we simplified the square root of 50 to 5 square roots of 2. That 7 and the 10 are still part of the problem. Okay. What would be our next step? Good, we could divide. What numbers are dividing here?
The 5 and the 10.
The 5 and the 10. So the 5 and the 10 divide because the 7 and the 10 couldn't divide. So 5 and 10 divide, leaving the 10 on the bottom to be a what?
5.
A 2. Because you do think 10 divided by 5 is 2. So there's 2 on the bottom. So now we have 7 square roots of 2 divided by 2. Can this simplify any further?
No.
No, this is our answer.